The next speaker will be Alex Filippenko. Alex Filippenko is a professor of astronomy and the Richard and Rhoda Goldman Distinguished Professorship of Physical Sciences at the University of California, Berkeley. He received his Bachelor of Arts from from UC Santa Barbara in 1979 and PhD from astronomy from Caltech in 1984. Major area of Alex's work is understanding application of supernova and the application to a range of problems involving, including, for example, central black holes and galaxies and cosmology. His team of robotic telescopes developed a robotic telescope at Lick Observatory that has discovered over 1,000 nearby supernova. Alex is the one person to have been member of both teams that revealed the accelerating expansion of the universe discovery that was honored with the 2011 Nobel Prize in Physics to the team leaders, as well as the 2007 Gruber Cosmology Prize and the 2015 Breakthrough Prize in Fundamental Physics to all team members. Alex has also made several outstanding contributions promoting physics, astronomy, education, and outreach, including serving as author and co-author on textbooks in physics and astronomy, and appearing in numerous television documentaries. Today, Alex is going to talk to us about the expansion of the physical universe. Let's welcome Alex Filippenko.
Well, thank you, Corbin, for that very nice introduction. It's a pleasure to speak here in this august meeting of people, mostly particle physicists, and so I thought I'd give you more of an elementary introductory talk in astrophysics and cosmology, detailing how the discovery was made of the accelerating expansion of the universe. So we've known for nearly a century that the universe is expanding based on Hubble's analysis of redshifts measured by Vesto Slipher, a person who gets far too little credit, and Hubble's measurements of the distances of galaxies. And as I'll show you later on, now with telescopes like the Hubble, we have a very, very good measurement of the current expansion rate of the universe. Here's an idealized Hubble diagram with no scatter, no noise, log of distance versus log of redshift, or recession speed, and the Hubble constant is basically the slope of that line. Now, if we plot the scale factor of the universe as a function of time, here I show the case of an empty universe with no gravity, the Hubble constant is just a dot over a evaluated right now. And it's just some number that corresponds to essentially the slope of that line divided by the value of the scale factor at this time. But you could have a dense universe that reverses its motion, a little bit like the trajectory of this apple, and right now it would have the same Hubble constant, the same a dot over a value. Or you could have a medium density universe. This is one whose average density corresponds to the critical density. In this case, of course, the recession speeds of galaxies asymptotically approach zero, all right? And in the early 1990s, observers measuring the distribution of galaxies and clusters of galaxies told us that what we live in is a lowish density universe, omega matter of around 0.3, in which case the recession speeds of galaxies would asymptotically approach some constant value, not zero. The question is, which of these universes do we really live in? Is there some other way to know? And there is a way to know. We can look at the past history and thus predict the future. So let's zoom in on that part of the diagram. Here I have A of t versus t, and I've got the three cases: an empty universe, a low density universe, a critical density universe, and a closed omega matter greater than 1 universe. And the point is that here we are now, redshift 0. Redshift is defined as 1 plus z is the scale factor of the universe at the time the photon we are now seeing was emitted, divided by, the scale factor now divided by the scale factor at the time that the photon was emitted. So redshift 1, for example, by advanced mathematics, 1 plus 1 equals 2. 1 over 2 is 2. So basically the scale factor of the universe was half of what it is now, when the photon from a galaxy at redshift 1 that we are now seeing was actually emitted. And you can see here that the look-back time will depend on what the history of the universe has been. For a given redshift, the look-back time, and hence the distance, is shortest in a dense universe, bigger in a lower density universe, bigger still in a low density universe, and the biggest possible in an empty universe, or so we thought. So by simply measuring the distances, and hence the look-back times, as a function of redshift, we should be able to tell the past history of the universe. So the observer's version of this diagram looks something like this. Distance determined by a method other than the redshift. It's not fair to use Hubble's law because we're looking far enough back in time that we're looking precisely for deviations from the Hubble law. So distance versus redshift. And you can see here that indeed the densest universe has the smallest look-back time, the smallest distance for a given redshift. So you populate this diagram with observations, and that tells you the future of the universe in principle. Well, how do we get the distances of these various galaxies? And how do we get the redshifts? The redshifts are easy, all right? You just measure the spectrum of a galaxy, and you see spectral features which you recognize in a very nearby galaxy whose recession speed is essentially 0. Here's the spectrum. Here's the same spectrum that I arbitrarily shifted by 1/10 of the speed of light. It's the same spectral features. You just measure the delta lambda, basically. All right? So that's easy to do. The distances are a lot harder, all right? I'm going to use distances that are called luminosity distances. There are many types of distances in cosmology. You get into trouble if you mix them. Stay with one distance. Luminosity distance is just that distance that exactly satisfies the inverse square law of light. So you measure a flux, a brightness, you somehow know the intrinsic luminosity, and that gives you the luminosity distance. The hard part is knowing the intrinsic luminosity. How do you do that? You need some sort of a standard candle. They don't exist, even though astronomers call lots of things standard candles. They're standardizable. In a nearby galaxy like this one, especially with a Hubble Space Telescope image, it's easy to see individual stars, at least the more luminous normal stars. And for nearly a century, what's been used are the Cepheid variables. They're still being used. They're recognized by their light curves. All right, they rise pretty steeply, decline more slowly with time. And they have what's called a period luminosity relationship. They're not all of a standard luminosity. But if you know the period luminosity relationship, then measuring the period tells you the luminosity, and you've standardized your candle. I call them standardizable candles, not standard candles. Anyway, this was first done by Edwin Hubble with the Hooker telescope above the San Gabriel Valley. He famously discovered a Cepheid variable in the Andromeda Nebula, basically showing that the nebula was an external galaxy, an island universe, so to speak. And so that's not so hard in nearby galaxies, at least not these days. But how about these galaxies, these little smudges, which are billions of light years away? Cepheids aren't luminous enough to be seen in such distant galaxies, so we use another technique, supernovae, exploding stars. They can become millions or even billions of times the power of our sun. And in particular, there's several types. And the one that's most useful for cosmology are the type 1As. You can see their spectrum here. They have all kinds of elements, but notably no hydrogen nor any helium, as opposed to the type 2s that do have hydrogen. So it's the type 1As that we've been using. They are thought to be standard or standardizable, both observationally and theoretically. Theoretically, they come from a white dwarf at or near the Chandrasekhar limit of around 1.4 solar masses. It approaches that mass either by stealing material from a more or less normal companion star, or perhaps double white dwarf mergers can occur. In any case, the less massive white dwarf, in this case, gets tidally disrupted by the more massive one, forms an accretion disk. And so the thing should still explode near the Chandrasekhar limit, even though in principle the sum of the white dwarf masses could exceed 1.4 solar masses, but you get this dynamical accretion such that the explosion still occurs at or near the Chandra limit. Well, they're pretty standard, but they're not exactly standard. This was noticed decades ago, but Mark Phillips noticed an interesting relationship from the ones studied in nearby galaxies. The intrinsically more luminous ones have slower light curves. He measured the decline rate, but now we know even the rise rate is slower than those of the normal ones. And then there are subluminous ones which rise and decline more quickly than the normal ones. And this technique was then perfected by Adam Rees in his doctoral thesis with Bob Kirshner at Harvard, and by Mario Amui in Chile and other people. And by perfecting this technique with a set of only 10 supernovae in the mid-1990s, and then applying it to other supernovae in galaxies of unknown distance, you could then figure out the distances of those galaxies. You use this technique to standardize the candle. The devil is in the details. You need to take into account interstellar dust and stuff, which can dim the supernovae for a reason other than distance. Okay, if there's fog in the way, the headlight will look dimmer. And so you measure the colors, and that gives you the reddening, the extinction, like the red setting sun effect, all right? And when all is said and done, this multicolor light curve shape method works remarkably well. Here's at the top there the Hubble diagram, assuming all type 1a supernovae are standard candles with some dispersion of, say, 50% or so. And then you apply the multicolor light curve shape technique to that same set, as determined from a set of about a dozen nearby well-observed supernovae. You independently then apply that to this new set, and the dispersion decreases by a factor of 3, making the type 1a supernovae enormously useful for cosmological studies, okay? It's fantastic. You see guys like this one, which look way too distant, and that's because that one was behind a screen of dust. And when you apply the correction, boom, it just falls right where it should. It's fantastic. So this is what makes supernovae 1a such useful cosmological yardsticks. So now the trick was to go and find them in lots of distant galaxies, and having calibrated their luminosities based on nearby galaxies, we could then get the distances and hence the look-back times of the distant galaxies. So in the early 1990s, 2 teams were formed. Saul Perlmutter at Lawrence Berkeley Lab and UC Berkeley formed one of them, the Supernova Cosmology Project, and Brian Schmidt and Nick Senseft formed the High Redshift Supernova Search Team. They weren't always at each other's throats. It was generally a healthy competition. Here we are in Aspen decades ago discussing our different ways of calibrating the supernovae. Having 2 teams accelerated progress, if you'll pardon the pun. Both wanted to be first. It improved the science because both wanted to be best. If one team were taking one technique into account and the other team were not, then that second team would look bad by comparison. And finally, and most importantly, had there not been 2 teams, almost nobody would have taken our results seriously, all right? Both teams used telescopes primarily in the southern hemisphere to take wide-angle pictures of the sky that have thousands of galaxies within them. You repeat those pictures 3 weeks later, subtract digitally the old images from the new images, and you find things that look like they might be new. Here, cleverly placed in the circle, is something that looks like it might be real among all the noise. And then my job on both teams was to use the Keck telescopes to get the spectra of these candidates to determine whether they really were type 1a supernovae, and to get the redshifts of the galaxies. Because remember, you need not only the luminosity distance, but the redshift. I'm a trained spectroscopist. I've been working on supernovae since the mid-1980s, and I have privileged access to these wonderful, wonderful telescopes. So here's a spectrum of one of these guys. At the top there, 1999 FF at redshift 0.455. You can see that to within the noise, it looks pretty much exactly like a 0 redshift type 1a supernova. So data like this made us very, very happy. All right, well, what did we find? Here are 3 spectroscopically confirmed supernova 1As, and they're faint. They look really, really faint. And you might say, well, what's the big deal? They're in these pathetic-looking faint galaxies. Here you can't even see the galaxy. Obviously, these are very nearby. And that's true. I'm sorry, obviously, these are very distant. And that's true, but the point is they're more distant than they should have been in any reasonably behaved universe, any reasonably behaved Newtonian universe for sure. So here are the possibilities that I outlined near the beginning of my talk, and the data actually fell there. In other words, at a given redshift, the supernovae were fainter and thus more distant than they should have been in any standard cosmological model. And we had to take into account the dust and the possible evolution of the type 1As. Maybe 5 billion years ago, they were intrinsically less luminous than they are now. We tried to take that into account to the degree possible. So, does that imply omega matter is less than 0? I mean, look, right? Greater than 1, 1.30, less than 0. Natural conclusion, but we don't know of any anti-gravitating people or anything like that. And it would have made Einstein kind of unhappy, probably. But he had come up in 1917 with an alternative, which he later renounced as his supposedly biggest blunder of his career, in order to account for an apparently static universe, which nearly everyone believed in back then. He conjured up this fudge factor, essentially a constant of integration, but one which he finely tuned to exactly negate the attractive effects of gravity and to give a static universe. This, of course, is mathematically unstable, and it has other problems. Why would there be this fine-tuning? He never liked it, but he felt compelled to introduce it in order to explain this apparent static nature of the universe. He later renounced it in 1929 when Hubble discovered that the universe isn't static. Anyway, he called it the cosmological constant. So instead of saying this is omega matter less than 0, let's call it omega lambda, the cosmological constant density of the universe greater than 0. That would be an alternative explanation. All right? And the data based on supernovae discovered prior to 1998 are shown here. This, again, is sort of proportional to the log of the luminosity distance versus redshift. And you see all these points at low redshift. That's the anchor. You need those. Otherwise, there's nothing with which to compare the high redshift ones. And they seem to go above this, Einstein de Sitter universe of omega matter is 1. And they're even above the low density preferred universe of the early 1990s. And here you can see the difference. And the data cluster above this omega matter 0.3 lambda equals 0 universe. It was only a 2.5 to 3 sigma result at the time, far from the 5 sigma rigors of particle physics. But look, we have one universe, and it's hard to gather these data. And if we didn't report this, we would have been scooped by someone else. So astrophysicists can't always rely on 5 sigma, all right? Sorry about that. We don't have the LHC with which to do trillions of collisions. But it looked pretty good, High Z data, fainter than flat or a low omega matter universe. And so here are the lambda matter contour diagrams published by these two papers. And you can get a lambda equals 0 universe, but most of the area of these contours is above lambda equals 0. And again, had there been only one team, I don't think people would have taken us very seriously. Here are the two papers that came out reporting this, and Einstein would have been pretty surprised if he were alive right now to see his cosmological constant idea resuscitated, not to give a static universe, but one which on large scales is cosmically accelerating. Evidence started building up from other sectors. The study of large-scale structure, which George mentioned in his talk, suggested omega matter is 0.3 plus or minus 0.1. The boomerang results came out around the year 2000, giving a flat universe. That was enormously useful as well. So here's the constraint from large-scale structure to a good first approximation. You get a vertical rectangle here. It's a little bit tilted, but to a good first approximation, it's vertical. And here are the microwave background constraints on a flat universe. And so the concordance cosmological model began to emerge, all right, and has grown in strength. This was really pretty radical at the time. No one liked the cosmological constant. But look, this is what the data seemed to be telling us. The results became even stronger with the beautiful WMAP maps that came out. Fantastic. So by around 2004, here's what the supernova contours looked like. Now, at the 4 sigma level or so, the supernovae alone are above omega lambda equals 0. And if you add the constraint that omega matter is 0.3, then you're really quite far above the lambda equals 0 line. And supernovae 1a plus large-scale structure gave a precision comparable to the CMB plus large-scale structure. In other words, you could say, I don't like type 1a supernovae. For some reason, they're giving the wrong result. Okay. But if you like large-scale structure in CMB, you get the same result. In other words, you now have 3 methods, any 2 of which give the same answer. So that's fantastic. And by this time, Einstein de Sitter was ruled out at many sigma. We then started probing the era of deceleration. If we live in a universe with lambda of 0.7 and matter of 0.3, then early on, the universe should have been decelerating because the dark matter would have dominated over any lambda component, and then it would go through this jerk where it starts accelerating. So you go way back in time to even higher redshift supernovae than the redshift 0.4 to 0.5 upon which the early results were based. And we found them with the Hubble Space Telescope, and we studied them. And here then again is log luminosity distance versus redshift. Here are the data. This is now becoming a real thing of beauty. And here are the data relative essentially to this dotted line. Here you see the reasonably recent acceleration in the past 5 billion years, preceded by deceleration. So that was fantastic because if, for example, the faintness of the supernovae had been caused by dust or supernova evolution up to redshift 0.5, then you'd expect even more dust and even more supernova evolution at higher redshifts. Whereas if this really is a cosmological feature of the universe, you'd expect it to start looking like Einstein de Sitter at early times. So this was a very important test. Other tests, well, you take this wonderful map and you use it as the initial seeds for cosmological density fluctuations, and you run them through a computer. With only dark matter, you get large-scale structure that looks kind of like our observed universe, but with dark matter and dark energy, you end up with z equals 0 large-scale structure that looks a lot better, a lot closer to what our actual observed universe looks like. So the growth of large-scale structure supports this lambda idea as well. And then there's X-ray clusters of galaxies. I don't have time to go through all of the supporting evidence. But basically, this is the diagram that emerged. This is a simplified diagram of what the 2 previous speakers showed. A 95%, or maybe as Rocky said, 98 point whatever percent puzzling universe, depending on whether you're really bothered by baryogenesis or not. But anyway, so here we are. This has been shown several times as well. We've got the birth of the universe for whatever reason, inflation, quantum fluctuations, and their stretching by inflation, leading to the seeds from which large-scale structure later developed. The universe for 9 billion years decelerated, then in the last 5 billion years or so has been accelerating. In a sense, a new era of inflation that we have entered. It's nowhere near as rapid, it's not exponential yet, but if the dark energy continues behaving in the same way, someday it will be exponential. And by 2011, 13 years later, there was so much evidence for this acceleration that the Nobel Prize was awarded to Saul Perlmutter, Brian Schmidt, and my postdoc at the time that we did this work, Adam Rees. And by this time, I was working primarily with Schmidt's team, although early on I had contributed significantly to Perlmutter's team. So that was really cool, and we all went to various lunches and galleries and stuff. And at this particular lunch, my wife sort of revealed her consolation prize to all of us who did not technically win the Nobel Prize because of the rule of maximum of 3 people. And it was a limited edition shirt. Dark energy is the new black. She sent this shirt to the King of Sweden along with a $2 bill saying, here are 2 items you are unlikely to already have. So anyway, and a few years ago, the Breakthrough Prize recognized all team members, recognizing that big science these days is done by teams. Okay, so since dark energy seems real, what is it? It's not necessarily the cosmological constant. As I said, a lot of theorists really don't like the cosmological constant, although I kind of like it. It argues for a multiverse. I'm sorry, George, I kind of like the multiverse, but, oh, there's George. We can duke it out later on. You know, but a lot of theorists don't like it because there isn't very good agreement with observation, with theory. Theory predicts an infinite vacuum energy, and okay, if you cut things off at the Planck scale, only 10 to the 120 power, and we measure 0.7. Okay, so, you know, Steven Weinberg said it's a bone in the throat, this thing that we discovered. So maybe it's not lambda, maybe it's something else. Define the equation of state parameter W to be P over rho C squared. Rho is proportional to the volume to the -1 plus W power. W is 0 for normal non-relativistic matter. W is 1/3 for photons because they stretch with the expansion of the universe. W is -1 for lambda. In other words, it's a vacuum energy that does not depend on the scale factor. And W is -1 for a whole class of models called quintessence, rolling scalar fields, whatever. As an example, -1/3 for cosmic strings, all right, which can be ruled out already quite easily. So in general relativity, gravitational acceleration is proportional to minus quantity rho c squared plus 3p. So all you need is a pressure basically that more than balances, a negative pressure that more than balances positive rho c squared, and you get a positive acceleration here. So that's what you need, W less than -1/3, and like I say, it's -1 for the cosmological constant. So let's try to measure what it actually is. This is not so easy to do. Here are the differences in magnitudes, and for the non-astronomers here, to a good approximation, 1/100th of the magnitude is 1% in the brightness of an object, okay? That's a pretty good rule of thumb for small numbers of magnitudes. 1/10th of a magnitude is a 10% variation. So you have to go and measure magnitudes of supernovae to the few hundredths of a percent in order to distinguish between W of, say, -1.1 and W of -0.9. That's starting to be quite hard to do because there are all kinds of things that can kind of bite you in the butt, all right? Nevertheless, it's been done. And one of the latest papers, there's new papers coming out, but is this joint SDSS and Supernova Legacy Survey analysis. And you know, you look at this Hubble diagram now, Edwin Hubble and Milton Humason would just be astonished by what we've achieved here now, 85 years or so after their original Hubble diagrams. They're just really things of beauty. So now you can plot omega matter versus, say, W. And again, you know, you use microwave background, and you can use baryon acoustic oscillations and stuff. And lo and behold, there's this pretty good concordance. And, you know, it does intersect W of -1, although most of the area is a little bit below that, which is a very weird sort of phantom energy whose energy density grows with time. Now, I don't for a minute believe that, okay, but, you know, we've got to do better. And in any case, we do have agreement with W of -1, omega matter of 0.3 or so. You could assume a time-dependent W, and there are various parameterizations you can use. For example, W of A is W naught plus W sub A times 1 minus A, where basically A is a function of the redshift. So for lambda, W naught would be -1, and W of A, the time derivatives, would be 0. Okay, so let's do that. Now, you know, you're taking a derivative, so we don't have as good constraints. The diagrams have a much bigger set of error or uncertainty contours, but still it's consistent with W naught of -1, WA of 0, right? So it's consistent. So far, the null hypothesis that this is the vacuum energy and not some rolling scalar field or something, you know, I mean, you might say that's a bad null hypothesis because you don't like a vacuum energy, but it's the simplest hypothesis, in a sense, right? So what have we been doing lately? We've been trying to measure this ever more precisely, measure the past history of the expansion ever more precisely, and my field is type 1a supernovae. There are other complementary measurements which are equally important, all right, in order to better predict the future. Is it something that's more negative than W of -1, in which case we'd get a big rip someday? Kind of a disheartening possibility. We'll all be destroyed. The atoms of which you are made will be destroyed someday. Again, I don't believe that. Constant dark energy, that would be lambda, or maybe some sort of a scalar field whose sign changes in the future. Happened at the end of inflation, so why not again, right? The inflaton turned into us, in a sense. Right? We all contributed to the Big Bang, is what I like to say in my public talks. So we've done this, and here's our most recent surprise, all right, in a set of papers published in the past few years, one of which just got accepted. The current rate of expansion still might be too high, even taking the standard model of cosmology, 70% lambda-like substance, 30% gravitationally attractive matter. Take it into account. What do I mean? All right, you take this Planck map, a thing of real beauty, all right, and you've got the angular power spectrum. It's incredible. I mean, my goodness, look at those data points, incredible. And so, you can define an angular diameter distance as basically the sound crossing horizon divided by these angles that you measure, all right, right there. And so from that, you can derive a Hubble constant, and you can basically use the standard model, 70% lambda, 30% gravitationally attractive matter, to predict the current expansion rate. And here's the Planck 2016 paper, H0 of 66.93 plus or minus 0.62. All right, great. Previous direct measurements by Wendy Friedman and others typically gave numbers in the range 70 to 75, plus or minus 4 to 7. Possible conflict, but it's not at all clear. The error bars are big, and the error bars themselves are uncertain, so nothing to write home about. So what we decided to do, my former postdoc, Adam Rees, and I, and others, over 10 years ago, was to launch a campaign to progressively more precisely and accurately measure the current value of the Hubble constant, all right? The goal is actually to measure it to within 1%. And we'll achieve that goal, we think, when the final Gaia data analysis comes out. And we do it with Cepheids. We calibrate the distances of the host galaxies of nearby type 1a supernovae, which are the anchor for the whole supernova 1a Hubble diagram. And the latest results, it's a preprint that's been accepted now, is where we include some Gaia data. And again, we're just using Cepheids to calibrate the distances of host galaxies of nearby type 1a supernovae. And the Cepheids we've found through Hubble Space Telescope pictures. They're in there somewhere. Pretty faint, but with Hubble you can do amazing things. And so what do we get? And here's our latest result, which strengthens things because we use Gaia parallaxes of galactic Cepheids, Milky Way galaxy Cepheids. We get H0 of 73.52 plus or minus 1.62. And there's the Planck value, 66.93 plus or minus 0.62. And we announced an earlier version of this several years ago, and people said, oh, you're full of it. But we weren't full of it in 1998 when we announced the accelerating expansion of the universe, so maybe we sort of know what we're doing. And even back then, we said, don't bet your life on it, don't bet your house on it. I'm still saying don't bet your life or your house on it, but nominally, there's a tension of 3.8 sigma now. And we're approaching particle physics 5 sigma. We're not there yet. The uncertainties are smaller than ever before, and we think we understand them very well. That's the crucial thing. We've examined our uncertainties very, very carefully, and we think that our uncertainties are reasonable. So maybe this is true. By the way, if you do take this value of 73.52 and lambda 0.7, matter 0.3, then in fact the age of the universe is only 12.8 billion years, not the 13.8 that everyone likes to cite based on a self-consistent Planck analysis. But by the way, the universe hasn't necessarily been measured by Planck at the 1% level. They give these tiny error bars, but I'm not picking a fight with George or anyone else here. I'm just saying this is a really interesting development that's strengthening with time. So here's, Mazur's, Sunyaev-Zeldovich effect, lensing, Tully-Fisher relationship, non-supernova 1A average. And then here's a set of results. If anything, our number is getting slightly higher with time. And here are error bars. And here's Planck. So what could account for this? Well, a non-flat universe, or time variable dark energy, or a change in the effective number of relativistic particles at early times. All right? So maybe more than 3 neutrino species. I mean, primordial nucleosynthesis and other arguments tell us that there are 3 active neutrino species, but maybe there's some sort of a sterile neutrino. Someone mentioned it yesterday, right? That would be pretty cool. Or maybe it's technique errors. That would really be boring, but if that's true, we've got to find out someday. And then maybe GR is wrong. Maybe there's weird dark matter that interacts with light. Who knows? Now, you may dismiss all this, but all I'm telling you is that over the years, the result has becoming stronger and stronger and stronger. It was 2.5 sigma some years ago. It's now all the way up to 3.8, unless we've done something wrong. Well, the way to test it is to use independent methods to overcome the possible systematics. And the one I want to mention is a very interesting one with which I have no personal or professional interaction whatsoever, other than reporting the results. Strong lensing of quasars by galaxies. You get multiple images of the same galaxy. The path lengths have different lengths, and they go through different gravitational potentials. So the time delays of the quasar brightenings are non-zero. And you can measure the time delays, and you know the geometry from the physics, and so then that tells you the overall scale, and so you get a Hubble constant. You can do this even better with supernovae, because they have much more step-like functions in luminosity than quasars do. We plan to be doing that in the next few years. So here's this holy cow result of several lenses, and they get a value of, I think it's on my next slide, 72.8. with slightly bigger error bars than what we have with type 1As right now, but they're getting better and better. And again, with strongly lensed supernovae, this will become even better. So that basically agrees with us. A local value of the Hubble constant that differs from the early time measurement and its extrapolation. So my own favorite is that it's some sort of a new particle that we haven't taken into account. The standard model hasn't taken into account because there was no reason to do so. But now possibly there's a reason to do so. I find this to be a more palatable explanation than dark energy getting stronger with time, or dark matter that somehow interacts with photons. And certainly I find it more palatable than GR being wrong, because how could GR being wrong? Well, that's my preference. Anyway, we don't know yet. But start paying more and more attention, because I think that this is a problem deserving of your attention. It's only growing with time. And I'd like to thank the various agencies and individuals that have funded this research. Thank you very much.
Well, thank you, Alex. That was great. We have some time for a question or two.
There's a bunch of them, so you choose.
All right, we'll start. Okay, we'll start there.
Hi. So I know this question might be kind of impossible to answer, but everyone always is like saying, "Oh, like the universe is expanding and stuff," but no one ever really says what it's expanding into. And I mean, I know that that's kind of like, there's not, I just was wondering if you had any like theories
what
or
is
anything
the
to talk
universe
about.
expanding into?
Mm-hmm.
It need not be expanding into anything. You can have a mathematically expanding universe that just the coordinate system expands in general relativity. But if that's too abstract, you think of it expanding into another dimension in a bigger hyperspace. And the example I like to give is a balloon, a two-dimensional closed universe. If you allow the laws of physics to only operate within the rubber of the balloon. It's a two-dimensional universe. You can go forwards and backwards, left and right, or any combination of those two motions, but you're not allowed to go in or out. Yet it's expanding in that radial outward direction into a bigger hyperspace, this room. So you can think of it that way, but mathematically you don't have to assert the actual physical existence of that other dimension. It doesn't have to expand into anything, just like the real number line can expand, but it doesn't expand into anything. It remains the same infinity.
I was just wondering, because there's still multiple scenarios for what exactly causes a type 1a supernova.
Yeah.
Does that ever keep you up at night or something like that?
Yeah, the issue that we don't truly understand the progenitor and to some degree the explosion mechanism of a type 1a does keep me up at night. We're making progress on that front, but at the very least we can say that empirically, if we use these empirical standardizations and all that, the Hubble diagram dispersion goes down at small redshifts and high redshifts when we do this. And so whenever dispersions go down, you build some confidence, but it'll be better once we truly understand the progenitors. And I actually think there are several mechanisms, both the so-called single degenerate model and the double degenerate model, and maybe even the dynamical interaction of a three-body system where two white dwarfs actually collide. But we're working on that, and it's a very important project. Yeah.
The Hubble constant measurement from gravitational wave events at LIGO. When is it expected to be?
Yeah. So another method will be, as I said here, we want as many. Oops, that was the wrong way. Oh well. We want as many methods as possible to independently test this. This, in a sense, historically, this is why the accelerating universe eventually became accepted by most cosmologists, not because of only 1A supernovae, but because of the concordance model. So the standard sirens of neutron star merging pairs, it's fantastic, right? You get from the waveform, you know exactly what kind of a system merged. And unlike the inverse square law of light, where it's diluting over the surface of a sphere, the amplitudes of gravitational waves are inverse distance. And so you know what the actual initial luminosity was, and you know what you measured with LIGO Virgo. And so that gives you a distance that's based on this siren, and you measure the redshift of the galaxy. So it's exactly what you need, a distance measurement that's independent of Hubble's law, so that you can measure deviations from Hubble's law. So that'll be a way of doing it. And the very first event, the one that went off that we saw in August of last year, gives a Hubble constant that's pretty much consistent with anything. Not with what de Vaucouleurs would have said 50 years ago, that it's 100, but it's within, I don't know, it's 70 plus or minus 10 or 12. So that one system is not yet very interesting, but when LIGO Virgo turn on again in less than a year, they should start finding more of these neutron star merging pairs, and so that'll be a new method with which to measure distances. Very important, yeah. Okay.
Great, well,
Okay, very good.
that was a great talk. Let's thank Alex one last time.